BA. BA is nothing but the maximum flux density. The average value of flux density in the duct is BA by 2. B average is equal to mu IT by 2LC. The radial forces acting on the strip situated at a mean radius r within an angle of coil is. So you can see DFR is equal to turns into flux density into current into length of strip. Therefore, the equation is given. DFR is equal to D T into B average into I into R into D theta. So it is the total equation for the total instantaneous radial force acting on the coil. In this, I upon Ex, I is the RMS value of full load and Ex per unit leakage reactance. On the worst conditions, on the worst fault conditions, the instantaneous value of current may become equal to the twice maximum value of current under short circuit conditions. So we can write I is equal to 2 root I upon Ex, where 2 is equal to doubling effect multiplier. So it is expression for maximum radial force under worst fault condition is. So here is the equation is given for maximum radial force under worst fault condition is. The second one expression is given while average radial force under normal operating conditions is. So the circular coils are preferred as are the strongest to withstand radial forces. This is because the tendency of radial forces is to make the coils circular, and as they are already circular, there is no deformation. So next is axial forces. In this in shell type of transformer, sandwich coil are arranged symmetrically. Now there is force repulsion between the coils of each pair. The pair is given 1, 2, 2, 3, 4, 5, 6, 4 pairs. The force on the coil 2 is opposite to that acting on 3. Similarly, 4, 5, 6, 7. So there is force acting on coils 1 and 8 only. So the average value of flux density in the winding is given, where T is nothing but number of turns in the end half coil. So you can see the expressions related to the axial forces. FA average is equal to mu upon 8n square IT square LMT upon W. It is the final equations for axial forces. Force due to asymmetry, unbalanced and axial forces. In the above discussions, winding considered were symmetrical, that is, axial height of winding is equal. However, tappings and manufacturing process of certain types of windings and non-uniform turn insulation causes axial symmetry between windings. The forces acting on the coil are given by, where K is equal to unbalanced factor, BPBS is equal to width of primary and secondary windings, and A is equal to width of duct. Here is bracings of windings. The former's packing pieces and core absorb the inward axial forces. The outward axial forces are absorbed by ending the insulation. All the interterm insulation and coil should be properly braced so that the mechanical shocks due to these forces are properly absorbed and withstanded. The end support should be mechanically strong. So I hope you have understood the radial forces, axial forces, the asymmetric forces. Asymmetric forces is nothing but unbalanced axial forces. Now there is question how to measure to overcome the effect of mechanical forces. To overcome the problems of mechanical forces, circular coil should be used for the windings as they can withstand with the radial forces. In circular coils, radial forces are cancelled by each other. Wherever it is not possible to use the circular coils, they should be braced properly. In shell type transformers, though coils are rectangular, they are mechanically strong as the larger portion of coils is mechanically braced. Apart from the bracing of windings, good quality of insulation is required electrically as well as mechanically. Coil should be supported and braced by taking into consideration of mechanical stresses. Also, asymmetry in magnetic field should be avoided. Tapping to be provided such that asymmetry due to this tapping is evenly distributed. The power transformer is designed to have high leakage reactance, which reduces magnitude of short circuit current during fault, hence reduces mechanical forces.